All right, good afternoon, everybody. As introduced, I'm Patrick Boughan from ISO New England. I've been working on what we call our economic studies, which are our long-range studies for about the last 5 years. I'm now the supervisor of that group. I can go to the next slide. Okay. I'll talk generally to begin with. So we had a large study called Future Grid Reliability Study that we spoke about last year that was a multi-year developed project from all of our stakeholders, in particular our state governments. And with that study, I talk about it now, is that basically we took half of the assumptions that we've used on these studies for years and threw them in the trash and made new ones. And by the end of that study, we took the rest of the assumptions and also threw them in the trash, and are now just doing an entirely new process. And I feel like that's a good summary of what it's like to work at an ISO right now, is that we're taking all the ways that we used to do business and just inventing it new again. Green button? All right. Thank you very much. So I'm going to blow through these first few slides. We're in the top right part of the country. These are our 6 states. We have generation and transmission lines as well. The one stat that's useful for the context of the rest of the presentation is that our all-time peak load is about 28,000 megawatts. At this moment, on the mid-70s rainy day in New England, we're at like 13,000 megawatts. So when we talk about the numbers of generation we're building, just kind of keep those in mind. This is what it looks like. We have DC ties with Canada, AC ties with also with Canada and also with New York. Generally, we have been farther away from coal. We've relied on oil as our fossil fuel of choice up until recently, and then we went along with everybody else and got really happy about natural gas. Then looking out to our 2040 studies is coming out of our future grid study from last year. We go back down to our 2000s-ish amount of natural gas, and that's almost all replaced with renewables. And the thing that's missing in this percentage graph for understanding is that the denominator of load changes dramatically, that we're about doubling what we're expecting in terms of overall system load. Currently, we're a summer peaking system. We expect that to change in the early 2030s to our winter peaking system, and that's almost entirely driven by heating electrification. And every state but New Hampshire is very excited to set goals for a transition. However, New Hampshire already has one of our nuclear power plants, so they're on board anyway. And our queue is full of a lot of things, mostly wind and storage and solar projects, and almost nobody's going to build a fossil fuel generator anymore. So that leads to, as part of saying that we threw away all of the assumptions about how we do these studies, is we actually changed our tariff about how we do these studies as well. We looked around the country and lifted from some of our sister ISOs, particularly in New York. We're now doing a repeated. Up until this point, it's been stakeholder driven what we do in these studies, and now, while the stakeholders still can submit requests under the new format, we're doing repeated 3 reference scenarios that I would talk about in a second, that are looking to essentially bring more structure and also make these more repeatable and comparable as we go through our study work. And as part of changing how we do this work, we also changed tools, and that's when we brought in PLEXOS 2 years ago. With our previous tools, we felt a bit constrained in terms of the reach for these new systems is so far from how we operate the power system today and it showed in the tools. The tools were optimized for a thermal grid, and it felt as if wind and solar and battery were like cool little add-on bells and whistles to the main thermal engine tool. And as we go to a renewable dominant system, the fact that those are add-on tools became a problem. And with the core design of PLEXOS of objects and constraints, it allows us a lot of flexibility as we look at these new systems. So this year's study is called the Economic Planning for Clean Energy Transition Pilot Study. We have extra flexibility this year to test out our new tariff language, and that flexibility has allowed us to look into different things that we have in our past studies. To some extent, our past studies have become like a little repetitive. That it was like, how much wind do you have here, and how much wind do you have here, and how much solar do you have there? And you get into like these minutiae of like little assumptions changes that take a lot of time to run. And ultimately, we had kind of done those for 5+, really a decade. And we wanted to move away from that same little like constant adjustments, but doesn't get you to actionable results. So with the new study, we've had more flexibility to do more of a deep dive into our overall assumptions. And as we're going to the results today, we're kind of zooming out, I feel like, to talk about the overall parameters of this change and where kind of like the hard endpoints are of the reality of this that you have to work with as part of doing this transition. So in this study, we have a benchmark scenario, which is we compare last year's real-time historical data to the simulated model data. We're essentially testing the fidelity of the model, make sure it works correctly before we go out into the future where we don't know the answers. And then we have a 10-year out case that's looking at, that's the end of our actual forecasted data. After that, we get into other creative ways of guessing the future in terms of load and demand. But in terms of the ISO's previous, ISO system planning used to always end at 10 years because that was plenty of times to build a thermal generator or a transmission line. But for this scale of transition, 10 years is not really going to do it. So we have moved beyond that to also look out at what we call our policy scenario, which we're saying is roughly 2050. The year doesn't really matter as much. It's that it's the end point of all the state policies and looking at what does that system look like. And then we have a slot where stakeholders can request things as well. And the policy scenario is where we're using the capacity expansion tool within PLEXOS. And also I feel like the most interest is for me. And that's what I'm going to focus on today. In terms of how we're doing the study, say that we view the LT tool not as a thing that can operate all by itself, but a thing that works in conjunction with the ST and MT tool. That we wanted to do a bit more of like trust but verify with the LT tool. So we step back and forth in time as we work through with the LT tool. We'll go maybe 5 years and then move to ST. Just thinking about it this way, that if you start with music and it's on vinyl records or like the original recording is the full quality, and then when you move to CDs, you went to a sampling method. And to the human ear, there's no difference between the record and the CD. And then if you go to an MP3, you get, initially the early ones weren't very high quality, so you can definitely hear the difference. But it's all different sampling methods, and now if you have Spotify and you like flip the right buttons, the audio quality is pretty good. And going to this morning's talk about the LT model from the founder here at Energy Exemplar, there's all different sampling methods, but we're not sure at this point, and we have to try out a few more that he mentioned this morning. But we're not entirely sure yet if those sampling methods are catching all the things we want to catch, so we step back and forth between the two. And again, just to give you, I find with our studies sometimes the outputs are interesting, but also sometimes just the inputs are interesting because we have this charge as a reliability, an RTO, ISO. We have specific responsibilities that are about planning the grid, operating the markets, operating the system. But realistically, at this point, with how policy is, we're the only central organization that's involved in climate change in New England, where our charge is not climate change, but since all of the things to prevent climate change are going through the electrical grid, we're effectively that central organization as well. And so just and one of the things we can do is take all these state goals and policies and just say what it all means. And so one of the things for us is just the net load. So remember I was saying that right now we're at 13,000 megawatts for today, and that our peak is 28,000. So by 2050, our peak becomes about 50,000. However, this is on a year time basis on the x-axis here, like stepping through the years. But you can see that we also almost touch 0 in the same year. So we need to build a grid that can both go to 50,000 megawatts and also operate at about 600. So we use the capacity expansion tool, and this is one of the build outs that we got. Our system favors offshore wind, primarily, then batteries, and then PV, and least land-based wind. But I want to caveat that land-based wind is actually what from our analysis so far, is essentially best value or best impact for our area. But the simple truth is we don't have enough space for it. There's a lot more ocean available near New England than land to put land-based wind on. And this is a very iterative process that we did with PLEXOS. Initially, when it ran, we would have different cutoff points of where things had to be built by, and left to its own devices, it'll wait into the year before and build like 15 gigawatts of wind in 1 year. And so we have build caps per year, and we call it like the glide path in order to have this happen in a way that could be feasible. We're looking at, I want to emphasize the x-axis here in terms of the capacity, that it's 36 gigawatts of offshore wind. Again, current peak load is 28 gigawatts. Today's is 13 gigawatts. And we'll have 26 gigawatts of batteries and 26 gigawatts of PV and 7 gigawatts of land-based wind. So we're talking about just a dramatic increase in our total nameplate capacity values of our overall system. And the annualized build cost is about $16 billion per year by 2050. And this is looking at a winter dispatch in 2050 for us. We did not retire any units that were not already retired. We just left them on. We figured the models wouldn't pick them. But on the 2050 year, we actually still need a lot of fossil fuels. This blue is natural gas. That black is actually coal. And I think we maybe have turned off our oil plants in this case, but essentially batteries are not enough. And this is another study we've done, that we just simply don't have time to charge them anymore with the heat. Basically the concept of storage for the shorter term, where you can charge it overnight like we do with pump storage and use it during the day or something like that, like a half and half, becomes like a 70-30 in the future with heating electrification. It's just like not time to charge anymore. And these are, our interfaces are congested. I'm going to skip by this because I don't think it's really that surprising. The current transmission system can't carry twice the power. So now we get to the slides I think are the most fun. So for this analysis, we're looking at 2032. So we step back. To some extent, we've studied into the future and we have 2050 results, and they are very interesting. And I'll talk about them a bit more. But we have to solve the near future, and I feel like that's where our focus is probably coming to look at 7 to 12 years out in order to make the way to the transition and keep things reliable and ideally affordable. So for this, we just wanted to this is part of giving the parameters of what the challenge is. We are looking at what amount of storage, likely battery storage, would you need in order to compensate for all of our existing oil, coal, and natural gas plants. In the interest in time, I'm not going to do a lot of the detailed explanation of how we did this, but it's in the slide decks, and I'm happy to talk afterwards. But it's mostly just with this, it's just converting energy types to a different energy type primarily. So we're looking at what we use in BCF per day or whatever the fossil fuel unit is and moving that to battery. So a couple notes to start with. We had in our future grid reliability study, one of our alternatives had 2.3 terawatt hours of battery storage, and that was not enough to get through the winter. At the moment, we have pump storage reservoirs that are good for 0.1 terawatt hours. And just a note that it's possible that these could be refilled along the way, but let's go into it more. So we're looking at a 7-day period. If we needed to how much energy would we draw in a 7-day period in the winter? And we looked, this is on a 20-year simulation, because we didn't want to, weather years are important when you get to a grid that's so dependent on weather for both your demand and your supply. So for 7 days, we need about 1 terawatt of hours of energy storage in order to get through a winter period. And when you go to 14, it roughly doubles. Some years are better than others. the weather profile starts to kick in here. You can see it better with the purple line standing out. But now we need 2 terawatt hours of storage in order to get through a winter period that is currently being provided by all these other alternate resources. And if we go to a 21-day period, we get up to nearly 3 terawatt hours. So it's whatever the storage mean is, and almost everything is energy storage, like DR is energy storage. So anything having Quebec hold back the reservoirs and trading power, that means energy storage. There's lots of options out there, but we do need a tremendous amount of it, and this is just for New England. But this is the parameters for us to look at, that if we're going to replace all this generation with other resources, that's how much storage we need to get through a winter period, about 3 terawatt hours. And then this is the other main point of interest for today, is we looked at what we called a levelized cost analysis in a few different ways. And here is where we stopped the simulation of LT every 5 years and looked at adding a gigawatt hour of a different resource, a gigawatt of each resource of different types, and looked at what sort of bang for buck payoff do you get with each of those resources. And it's based on net present value, which is in the formula at the bottom here. So this first chart, we're looking at for each dollar that you spend, what do you get in carbon reduction per ton for each resource type? And so it starts out here with, you get pretty good bang for buck on wind and PV, but not batteries. Because at this point, when you install wind or PV, you're getting decent capacity factors in terms of we're not curtailing that generation very much, and you are reducing carbon almost directly. Batteries look really terrible. That's $5,000, actually a little bit higher than $5,000 per carbon reduction ton, because in the initial years, we still have so much fossil fuels in the system, you're just arbitraging gas versus gas with batteries, so you're getting almost no reduction from the batteries. And we get into this middle period where all the technologies have a pretty good bang for buck. And then you get out to a place here, and there's going to be another chart that kind of brings this together in a few slides. What happens is you run out of hours where there's still carbon generation on the grid, and trying to hit that target with intermittent generation becomes extremely difficult. And so batteries, at that point, become one of our better technologies. Land-based wind is still great, but we wouldn't have anywhere to put it. But overall, these intermittent generators it's very difficult to target the hours you want to get the carbon reductions. You get up to, for PV, it's $4,500 per 1 ton of carbon that you reduce. And then this is a similar trend analysis, but this is looking at dollars per megawatt hour in terms of how much energy you get out of the unit. And the other key thing that's happening at the far right end of the side of this chart is that for everything we build at that point of wind and solar, we're curtailing it 96, 97% of the time, because we have too much most of the time. And it's only that little bit that's actually helping us reduce carbon. And so these next 2 charts will kind of tell the story of what happens over our carbon profile and why those last 2 charts exist. So initially in 2025, we have a lot of carbon generation in the summer. We have a bit in the winter too, but basically natural gas is coming on in the summer to help serve the load. And then gradually, as we put in lots and lots of renewables, we essentially have no carbon generation for 6 months of the year. But it's the winter that we're now trying to target with the remaining things to get to 90%, 100% renewable. And so this tells the story of duration curves and hours. Essentially, we're down to less than 10% of the year where anything that we're adding is useful. So it has to be able to hit that target in order for it to get to that last 10% or so. So the premise is, if you're going to do this transition entirely with wind, solar, and battery, the last 15, 10% of getting to renewables just gets very expensive because of this premise. And we're going to add in resource adequacy analysis and high-level transmission. but we're just looking at if all of our neighbors are decarbonizing on the same time frame, and particularly if we're trying to build all these things at the same time, then you get into things that are normally outside of our usual scope about like competition for resources, where we're also further drive up costs. And so we're starting to look at what else can we do if this is how the math looks at those edges, what is possible solutions instead? And that's essentially where we are in the study right now. We've established all of this, and now we're going to switch to using PLEXOS to try to imagine what are other possible solutions. And just a note for when this goes online, after the questions mark slide, there's a lot of other resources, including more information on the analysis, and also our 1 and 2 page, our full report, but also the 1 and 2 page summary on the last study that we did. Thank you very much.